Hello, welcome to the lecture series on vehicle dynamics. In this session, let us discuss about bounce and pitch frequencies. So, we will be discussing about bounce and pitch vibration modes of a vehicle, and we'll arrive at bounce and pitch centers to achieve the required bounce and pitch frequencies. So for that, let us model the car in a longitudinal direction. See, now if you consider this as a car, for our bounce motion, we consider only quarter car model. For pitch and bounce, we have to consider half car model. This is x-axis, this is y-axis. Okay, in this plane, this is z-axis and this is x-axis. There are two degrees of freedom. One is z degree of freedom, another one is theta degree of freedom. And we'll make some assumption. For simplicity in analysis, tire and suspension will be considered as a single stiffness, right. And damping and unsprung masses will be neglected. So we have to define this. We'll come back to this part later. Okay. Let us develop the models, differential equations. First, let us model in bounce degree of freedom, that is in the z direction. So I'll draw the free body diagram. This is shown in the upward direction, so inertia force should oppose this. I'll write mz double dot, then kfz, so it should act in this direction, so kfz. krz should also act in this direction, so fine, right. Because of theta displacement, one side spring may be stretched, another side spring may be compressed, so this is theta. If this is C, means this will become C theta. So it gets compressed, so it will try to act in this direction. This is B theta. So B theta, it gets stretched, it will try to act in the downward direction. So Kf B theta, and this one is Kr C theta. So we have got the equations. Correct. Here this gets compressed, so open up, yeah, this acts in one direction, the other one should act in the opposite direction, right. Correct. So maybe I can assume the other way also, no problem at all, right sir. So this is in one direction, this is the other direction, that's why you'll get minus sign here. Correct now? So this is Kf plus Kr, that is fine, absolutely no problem. Here by chance this side gets compressed, this will be acting in the opposite direction, this force stretches, this force will be acting in this direction. So these two forces are acting in the opposite direction, that's why minus sign here. Okay, so then divide throughout by m, and this part you can call it as alpha, and this part you can call it as, say, beta. Okay, fine. So we have got one equation. Next, let us model this in the pitch degree of freedom, theta. So instead of mass m, I should take mass moment of inertia, that is mk square theta double dot. Inertia force is given by J into alpha. J is nothing but mk square. Alpha is theta, then theta dot, then theta double dot. Yes, that's fine. Let us look at moment due to the springs. What will happen? One is, let us look at this way. Okay, this part is b theta. It is compressed. So force will be like this. So kf b theta is the force. Kf b theta is the force multiplied by b. Okay, multiplied by b. You are going to get moment like this. Here it is stretched. Correct. Then the force is what is this? Kf b theta is compressed. The force is like this. This will be this. This is kr c theta is the force. Kr c theta is the force multiplied by c again. Correct? And this will become kr b theta into b means kr b square theta. Kf. Okay. This is kr c square theta. Both are in the same direction. This force will be like this. Force into this tissue. This is the moment. So both are clockwise moments. Fine. Next, let us see kfz. Kfz is the force. So both are moving in the direction kfz, kfz. Kfz into b will create this moment. Krz will create counterclockwise moment. So one is positive, one is negative. So this is the way, right? Okay, fine. Write this and reorganize. You can take one positive, maybe clockwise, counterclockwise. You can take positive, clockwise negative moment, and you can do this. Okay, fine. Then I got the equations, two equations. For this equation, this is the solution. Assuming for this equation, this is the solution. Then differentiate, 2 times you differentiate, substitute for z double dot z and theta. Similarly, theta double dot you differentiate and substitute z, you substitute. Then reorganize. So from the first equation, I can take z by theta is equal to this. Second equation, I can take z by theta equal to this. When left hand sides are equal, right hand sides must be equal. Then we get this. Then if I open up, I'll get this equation. It will become fourth order equation. So let me reduce this as a second order equation. Assuming w omega square is equal to some other omega, I will do that. So then I will get a second order equation using minus b plus or minus under root b squared minus 4ac by 2a. I'll get this. Okay, so out of that, let us say one frequency is this frequency and another one is this frequency. Okay, all right. These frequencies always lie outside the uncoupled natural frequency. Okay. The oscillation centers can be found using the amplitude ratios of equation 10 and 11 with the two frequency omega, equation 16 and 7. Substitute will be found that will have opposite signs. The oscillation centers can be found using the amplitude ratios of equation 10 and 11. Okay, 10 and 11. With the two frequencies omega 1, omega 2 in equation 16 and 17. When substituted, will be found that z by theta omega 1, z by theta will have opposite signs. Okay. Suppose if I substitute here omega is equal to omega 1 bar 2, what I get? Then if I substitute omega is equal to omega, okay, the second frequency, the first frequency I'll substitute, and here second frequency of substitute, that is minus b plus or minus, another one is minus b minus. So those frequencies I substitute. So I call that as omega 1, that is omega 1, I call it omega 1, omega 2. That means here, let me write omega 1, if I substitute, I'll get omega 2 if I substitute, right? Okay. So when substitute, it will be found that z by theta omega 1 and theta will have opposite sign. That means when z by theta is positive, both z and theta must be positive. Both must be positive or negative. Thus, the oscillation center will be ahead of the center of gravity by a distance x equal to z by theta. Similarly, for the front with a negative value for z by theta, the oscillation center will be beyond the center of gravity by distance x equal to z by theta. So let us consider this is your vehicle. This is x-axis. Okay. This is my center of gravity point, CG. If z by theta is positive, both z and theta must be both positive or negative. So when the oscillation center will be ahead of the center by a distance x equal to z by theta. X z by theta, correct now? Or you can say z is equal to x theta, we can write. Or you measure z here, this value can be x, which is equal to z by theta, or it can be here. Okay, x here or here. Somewhere I just put the outside, like one distance will be large, likewise one distance will be large enough that the oscillation center will fall outside the wheelbase, and the other will be small enough that the center falls within the wheelbase. Okay, if you consider this is front wheelbase, this is rear wheelbase. Color let me change. So one should be within the wheelbase. This is center of gravity. One should be outside the wheelbase. Okay. One distance will be large, that the oscillation center will fall outside the wheelbase, and the other will be small enough that the center falls within the wheelbase. When the center is outside the wheelbase, the motion is predominantly bounce. So whatever frequency I get for that, here you are getting negative, that frequency is bounce frequency. And here I'll get, sorry, not here, this one, pitch frequency. Okay, for the center within the wheelbase, the motion will be predominantly pitch, and associate frequency is the pitch frequency. Okay, so this you can call it as bone center. Okay, then this one you can call it as pitch center. Okay, so this is what predominant modes. This is the center of gravity, it's the pitch center, this is the bone center, right? Okay, good. So clear? For one particular frequency value, Z by theta both will become, say, F plus. So X equal to Z theta, we can measure from here and we can mark that center. Another for weather value, it will become negative. So this is what you call it as bone center, and this is what you call it as pitch center. The corresponding frequency is called bounce frequency. This you call it as pitch frequency. The locations of the motion centers are dependent on the relative values of the natural frequency of the front and rear suspension. Okay, front natural frequency, this is the rear natural frequency. Okay, now here I have got a plot. Motion center locations. Motion center location means pitch center and roll center. Roll center. Okay. Now I said here front and rear natural frequency, that is F by FR. If FF is smaller than FR, ratio is less than 1. Then if I draw a line, so then from here if I drop a point, sorry, vertical line I have to draw, here you get and here you get. So this is where you are going to get the roll center, correct? And this is where you get the pitch center. So to get the roll center beyond the center of gravity and pitch center within this and ahead of center of gravity, then the frequency, natural frequency of the front, okay, ride rate, front ride rate frequency must be less than the rear ride rate frequency. Then only we can have this. Okay, so if you look at any one of the vehicle. This is the frequency in the front and this is the frequency in the rear. The ratio is here. Correct. So 1 by 1 to here rear by front here. Here front by rear should be less than 1. So everywhere it is like this. Okay. The vertical line, spring center, the vertical line which a vertical load, the vertical line which a vertical load applied to the sprung mass will produce only uniform vertical displacement. Correct. Okay. Apply a vertical load. Sprung mass will produce only uniform vertical displacement here. Parallel spring describes the suspension of a vehicle in which the effective static deflection of two ends are equal. Describes the suspension of a vehicle in which the effective static deflection of two ends are equal, that is the spring center passes through the center of gravity of the sprung mass. Okay. Okay, right. Maurice Foley, one of the founders of modern vehicle design, established a guide. So what exactly I want to say about all this kind of a thing is that the front suspension should have a 30% lower ride rate than the rear suspension. Or the spring center should be at least 6.5% of the wheelbase beyond the center of gravity. That is what he is trying to say. Okay, right. So another very important thing is that, right, that is very important. So in other words, to get good ride, the roll center should be beyond the center of gravity on the ground, and the pitch center should be between the front axle and the center of gravity. That's what it means. And for that, keep the front suspension softer than the rear suspension. Okay. So that the spring mast will be located. That's what it means. Okay. Another very important point is that why it should be located like that. There is something like what you call it as pitch frequency. You read all this. The overall meaning is only this. Pitch frequency, and another one is what you call it as bounce frequency. Of course, there is roll frequency also. The pitch frequency or bounce frequency should be, neither frequency should be greater than 1.3 hertz. That's very important. So this is what exactly provides the comfort to the occupant. Because many parts of the brain here, correct, will have a natural frequency. Okay, natural frequency lying between 2 hertz to 8 hertz. So our forced frequency or induced frequency should be less than this or outside this range. That's very important. So this can be achieved, then only you will get the comfort. So to achieve that, this pitch bounce center should be as specified. Okay. Another very important thing is that what should be this wheel-based length? That is the another important thing. We should act each point as a, what you can call it as, center of percussion, located at its one center of percussion. What do you mean by center of percussion? If I take a cricket bat or hammer, whatever it is, suppose if I ball hits over here and somebody is holding over here, the reaction is 0. Or if you are holding here and hit it here, reaction is 0. That means if I take this as a compound pendulum and if I hang at this point, oscillate, if I find a time period and reverse I do it and hang and find again, oscillate and find a time period, both will be equal. Then this is called centers of percussion. So whatever reaction happens at this point should not happen simultaneously at the point so also, right? That means to say, you see here, if you do not place the suspension, this distance properly, suppose front wheel has hit a bump or whatever it is rising. After some time, L by T time, this will hit this bump, then it will start rising like this. Correct? One is about to die, the other will come. Again it is about to die, this will rise. This is what exactly happens. So if I can do it properly, then you see here, one is about to fall. Yeah, this here it is rising, then falling. That time it will rise. Correct. But after some time, it's adjusted in such a way, both will start oscillating together, like they will be in phase together. Then finally it will die down like this. So this can be achieved only if di is equal to k squared by bc equal to 1. Okay, this is what we call it as dynamic index should be close to unity. Correct, otherwise it will set into too much of pitching like this. Okay, so this is what the meaning of these parts. So in summary, design the system in such a way, one is roll frequency, pitch frequency and bounce frequency all should be less than 1.3, less than or equal to 1.3. That's one important. Hertz. That is the main thing. So for that, 3 important things you have to do, like see that the pitch center always lies between the center of gravity and the front axle, and roll center lies on x-axis on the ground beyond the center of gravity. And the second thing is dynamic index k squared by bc must be equal to 1. That's very important. Another this thing is to achieve this, the front frequency, roll rate frequency must be smaller than a real roll rate frequency. This should be softer than this. In addition to this, you see roll frequency is also lies below 1.3. That's very important. So this is the summary of this pitch and this spring rate. Pitch and bones and pitch frequencies. Okay. Hope you understood about this. Now let me stop at this point. Thank you very much.